Dear students, so in previous class we were discussing about the uniform continuity of a function. So we say that if f and g are uniformly continuous functions, then f plus g is also uniformly continuous. Now come to another theorem. That's an important result, that A is a part of R. Let A is a part of R. F and G are uniformly continuous on E. F and G are uniformly continuous on E. Then, if F and G are bounded, if F and G are bounded on E, then the product Fg is uniformly continuous on E. So this is the result. So in previous class we see that f and g are continuous, then f plus g is continuous. There is no such restrictions. But here, if any two uniformly continuous, suppose f and g are uniformly continuous functions, then their product is uniformly continuous only when they are bounded. So the boundedness is a crucial condition. F and g are continuous, uniformly continuous, then f plus g is continuous. There is no such restriction. But here, the product of any two continuous functions, uniformly continuous functions, are uniformly continuous only when the two functions are strictly bounded. So come to the proof. So it is given f and g are uniformly continuous on E. F and g are uniformly continuous on A means there since f is uniformly continuous on A, f is uniformly continuous on A and g is uniformly continuous on A. Before going to that, f and g are bounded. F and g are bounded. That means there exists m greater than 0 such that modulus of f of x less than or equals m and modulus of g of x also less than or equals m. Okay, why? Because of the boundedness of these two functions. Now, f is uniformly continuous. F is uniformly continuous on A means there exists delta 1 greater than 0 such that modulus of f of x minus f of y is strictly less than some epsilon by 2m. Epsilon by 2m provided modulus of x minus y strictly less than delta 1. G is uniformly continuous. G is uniformly continuous on A means there exists some delta 2 greater than 0 such that modulus of g of x minus g of y strictly less than epsilon by 2m provided modulus of x minus y less than delta 2. Now, setting delta equals minimum delta 1 delta 2. Delta is minimum delta 1 delta 2. Then clearly these two equations are held for this delta. Okay. Thus, if modulus of x minus y less than delta, then modulus of f of x into g of x minus f of y into g of y. Then to show f is uniformly continuous, we have to show that modulus of f into or f of x g of x minus f of y g of y is strictly less than epsilon. Okay. So this can be rewritten as this equals modulus of f of x minus g of x. It is f of x into g of x minus f of y into g of x. You can introduce a new term f of y into g of x. So plus f of y into g of x minus f of y into g of y. Clear? So by the property of modulus, it is modulus of f of x minus g of x minus f of y into g of x. So it is f of x minus f of y into modulus of g of x. Here in first two terms g of x is common. So it is modulus of f of x minus f of y into modulus of g of x plus second term. Here it is modulus of f of y g of x minus f of y g of y. So it is modulus of f of y into modulus of g of x minus g of y. Okay. So, but modulus of f of x minus f of y is strictly less than epsilon by 2m. So, it is strictly less than epsilon by 2m into mod g of x. But mod g of x less than or equal cm plus modulus of f of y. That's again less than or equals modulus of f of x less than or equal cm. For all x fallen a, that means modulus of f of y less than or equal cm for all x fallen a. Why? Because x comma y are chosen from where? They are chosen from the same domain A itself. So it is again, it is plus m into, again it is mod g of x minus g of y, also strictly less than epsilon by 2m. So E equals m and m cancelling each other equals epsilon. That means if modulus of x minus y is strictly less than delta, then modulus of f of x into g of x minus f of y g of y strictly less than epsilon. That means f g or f of x into g of x is uniformly continuous on E. So the proof is finished. So the proof is heavily depends upon the boundedness of these two functions f and g. If f and g are not bounded, then the proof is incomplete. Why? Because the modulus of f of y and modulus of g of x, so there is no observation about this mod g of x and mod f of y, so you cannot complete this proof. So the proof is heavily depends upon the boundedness of these functions f and g. So that is the crucial point. Means if any two functions are uniformly continuous, then their sum is uniformly continuous. But if any two functions are uniformly continuous, then their product is uniformly continuous only when the functions are bounded on the given domain. So that is the crucial point, that is the importance of this result. Agree? Okay. Now, so we say that if f and g are continuous, uniformly continuous, then f plus g is uniformly continuous. Moreover, if they are bounded, then their product is uniformly continuous. So what about the composition of two uniform continuous functions? What about the uniform continuity of composition of two uniform continuous functions? Means my question is, if f and g are any two uniformly continuous functions on A, what about their composition? F composition G, is it uniformly continuous on E? So consider f and g are uniformly continuous on E. F and g are uniformly continuous on A for if f is uniformly continuous on F is uniformly continuous on E. That means that epsilon is positive, or for all epsilon positive, there exists some delta positive such that modulus of f of x minus f of y strictly less than epsilon provided modulus of x minus y less than delta. Agree? So for this delta, there exists some delta dash greater than 0. For this delta, there exists some delta dash greater than 0 such that since g is uniformly continuous on A, so it is modulus of g of x minus g of y strictly less than some delta, not delta dash, some delta provided modulus of x minus y less than delta dash. No need of confusion. F is uniformly continuous on A, then by definition of uniform continuity, for all epsilon is positive, we can find out a delta such that modulus of f of x minus f of y less than epsilon provided mod x minus y less than delta. Then that delta is fixed. If you fix in that delta, there exists another delta dash that is positive with the mod g of x minus g of y less than delta. Why? Because we have this g is uniformly continuous. Because this g is uniformly continuous. So if you fix in delta instead of epsilon, you fix this delta. Okay, delta is again sufficiently small positive quantity. So instead of this epsilon, you can fix up this delta. Then there exists another delta dash with a mod g of x minus g of y less than delta provided mod x minus y less than delta dash. That is why, because of the given function, g is uniformly continuous in the given domain. So consider these two results. This is equation 1 and this is equation 2. So combining these two results, then you have modulus of x minus y less than delta, starting from here. Modulus of x minus y less than delta dash, comma, we have modulus of g of x minus g of y less than delta. Modulus of g of x minus g of y less than delta. So instead of x, g of x. Instead of y, g of y. So this should implies, if mod x minus y less than delta, then mod f of x minus f of y less than epsilon. Here, if mod x minus y less than delta dash, we know that mod g of x minus g of y less than delta. Instead of x, here it is g of x. Instead of y, here it is g of y. So this should implies modulus of f of x minus f of y should strictly less than epsilon. Agree. So that means that implies modulus of instead of x, here it is g of x. So it is f of g of x minus f of g of y strictly less than epsilon provided modulus of x minus y less than delta dash. Okay, that means modulus f of g of x means it is f composition g of x minus it is f composition g of y. It is strictly less than epsilon, provided modulus of x minus y less than some delta dash. So what's your conclusion? So that means f composition g is also uniformly continuous. Okay, so there is no such restriction. Means here in this research we say that from these three results, f and g are uniformly continuous, then their sum f plus g is uniformly continuous. Also, their composition is uniformly continuous, so there is no such restriction, no restrictions, or there is any restriction, without any restriction. But the product f g is continuous only when, uniformly continuous only when they are bounded in the given domain. So that is the remembering point. Okay. So see, f plus g is uniformly continuous, f g is uniformly continuous, moreover f composition g is uniformly continuous. Now, if f is uniformly continuous, next come to another result here. If f is uniformly continuous on A, where A is a part of such that mod f of x greater than or equals k, comma, k is positive. Mod f of x greater than equals k, where k is positive and for all x is falling. Then 1 by f is uniformly continuous on E. Your function is uniformly continuous, then what about the reciprocal of that function? The theorem says that the reciprocal of a uniform continuous function is uniformly continuous only when that function, the modulus function or the absolute value of that function greater than or equals some or particular constant k itself. Again, there is a restriction. If it is uniformly continuous, we need not be say that 1 by f is uniformly continuous in the given domain. So the reciprocal of f, if f is uniformly continuous, then 1 by f is uniformly continuous on the same domain only when mod f of x greater than or equals some a itself. That is the restriction. It is same as the restriction. We say that there is a restriction in the product of G. The boundedness of f and G is the necessary argument. Here, the necessary argument is mod f of x greater than or equals k, where k is positive. So, now come to the proof of this theorem. How to prove this one? To prove 1 by f is uniformly continuous, we first consider 1 by f of x minus 1 by f of y. Starting from consider 1 by f of x minus 1 by f of y. What do you get? On taking LCM, it is modulus of f of x minus f of y minus f of x divided by modulus of f of x into modulus of f of y. Okay. Modulus of f of y minus f of x, that's same as modulus of f of x minus f of y. By mod f of x into f of y, that can be rewritten as mod f of x into mod f of y. Okay. But what is mod f of x greater than or equals k? So what is 1 by mod f of x? Less than or equals 1 by k. For all x fall in A, since y fall in A, for all x comma y fall in E. Since y fall in A, 1 by f of y also less than or equals k. So it is less than or equals 1 by k square, 1 by k into 1 by k, 1 by k square into modulus of f of x minus f of y. Okay. But what is f? Since f is uniformly continuous, f is uniformly continuous on E, that means for all epsilon positive, there exists some delta positive such that modulus of f of x minus f of y strictly less than epsilon, provided mod x minus y less than delta. Okay. So, if mod x minus y less than delta, then modulus of 1 by f of x minus 1 by f of y less than or equals 1 by k square into, but what is mod f of x minus, it is some k square into epsilon. Less than or equals 1 by k square into, what is mod f of x minus f of y? It is less than k square epsilon. That's only for the sake of arguments. Okay, so it is strictly less than k square epsilon. So that means it is strictly less than 1 by k square into k square epsilon means epsilon. That means if modulus of x minus y less than delta, then modulus of 1 by f of x minus 1 by f of y strictly less than epsilon. So that implies 1 by f is uniformly continuous on E. Okay, so when f is uniformly continuous, then its reciprocal function 1 by f is uniformly continuous only when mod f of x greater than or equals A itself. Clear? So, now let us discuss an important result. If f is continuous on a bounded subset A of R, if the theorem says that if f is continuous on a bounded subset, A of R, then f is bounded on E. Then f is bounded on E. So this is an important result. If f is continuous on a bounded subset of A, then f is bounded on A. F is continuous on a bounded subset of A of R, and f is uniformly continuous. If f is uniformly continuous on a bounded subset A of R, then f is bounded on A. So the proof is heavily depends upon the boundedness behavior of this A. When a set A is bounded, then it can be covered by, or it is as A is bounded means it is covered with the family of many balls of some radius positive. Means if set A is bounded means it is covered with a finitely many ball of radius, some delta or epsilon, whatever may be. So using that behavior of this A, or using that behavior of the boundedness of A, then we prove this theorem. So the theorem is very important. So the proof is in the next class. Thank you.